Okay, so hello everybody. Nice to have you on board for this new webinar of the IAVCEI series. We started in April 2021 the series of webinars, and of course, due to the COVID pandemic, but also the interest of many people worldwide, these webinars got a great success, and we are very happy with that. And they, in particular, they promoted the renewal membership of many people, or the arrival of new young members within the IAVCEI, and we're very happy with that. Today, today we're pleased to welcome a webinar given by Jorge Romero Moyano, who will present us the results of his studies for quite a lot of years, and was together with results from other authors on explosive volcanism in the Southern Andes, and as a natural laboratory to study explosive volcanism. And this will be very interesting. Of course, that's a very active region in the world, volcanic region. And we are very, very interested in the results presented by Jorge. I remember you that we have about 2 hours for this webinar. Maybe the presentation by Jorge will be something like 45 minutes, maybe. And you have the space Q&A to write your questions and for the discussions after his presentation. Unfortunately, I have another web meeting at 6:30 p.m. local time in Paris, so I couldn't stay until the end. But I wish you good time, and Jorge, it was great pleasure to listen to you. So I give you the word now, and good luck. Thank you.
Thanks so much, Patrick, for this presentation. I will share my screen, and we'll try to start as soon as possible. Okay, great. So should I start? Just
Yes, please. I think you can start.
Okay, thank you so much. So thanks everyone for attending this presentation. For me, it's a real pleasure to offer this talk, and I deeply appreciate the invite by Mattia and Daniele for giving this talk. So this presentation is focused on the explosive eruptions that have occurred in the Southern Andes in the last 15 years. But it aims to contain a summary of the valuable research that somehow has changed the lectures on explosive volcanism overseas. It is my personal belief that the Andes are such an amazing natural laboratory, and will love to tell you why and get you involved in the amazing and quite recent research that outcomes that we have from this part of the world. So I have to mention that this is not totally my research, is about what it has been done by several groups as well in the Andes, and I hope you enjoy it. So first of all, I will show you the contents. I will talk about the Andes as a mountain range. Then I will go into the Southern Andes with its tectonic setting, geography, ecology, culture, and the Southern Andes explosive volcanism. And then I will focus on the recent eruptions, the activity since 2008, and the personal, economic, and material impacts of those eruptions. Finally, I will try to prove that this is a natural laboratory with examples from the basaltic to rhyolitic volcanism and the Teflon outcomes that we have been producing during this time. And finally, I will give you the perspectives of a growing legacy on volcano monitoring, scientific collaboration, and multidisciplinary science that can be done from the Andes. So the Andes is a continuous mountain range of more than 7,500 kilometers long that extends along the west margin of the continent from the Caribbean to the southernmost end of South America. This destructive margin is controlled by the subduction of the Cocos, Nazca, and Antarctic plates from north to south beneath the continent of South America. The foundational rocks are composed by Pre-Andean basement blocks, Mesozoic to Cenozoic basin sediments, and the orogenic belt, which has mostly formed since the late Oligocene, when the Farallon plate fragmenting, forming this Nazca plate, accelerating the convergence rates dramatically. The volcanic arc in this part of the world appeared at least 185 million years ago. Currently, this volcanic arc is subdivided in 4 different regions, which are characterized by different architectures, I will say, of the subduction zone. The northern, central, southern, and austral volcanic zones. From those zones, I think, and is probably correct in terms of the number of eruptions that we have experienced, that the Southern Andes are the most active region of this area. So in general terms, the Southern Andes are characterized by the subduction of the Nazca plate, which is not very old. It is about 45 million years old in the oldest part of the plate. And this is subducted at a rate of 7 to 9 centimeters a year. And the subduction angle in this part is around 25 degrees, and the crustal thickness of the continental plate is between 30 and 50 kilometers. There are more than 60 historically and potentially active volcanic edifices in this part of the Andes, and of them 3 giant silicic caldera systems and numerous minor eruptive centers. So a part of the volcanoes that we can find in the Andes, we can observe a lot of major structures that seems to control the occurrence of those eruptive centers. So from those structures, I will say that the northeast and east-northeast trending structures usually represent tension fractures, extensional shear fractures, or tail cracks, and they source generally the more primitive volcanoes than in comparison to those aligned northwest or using ancient structures. So these structures are the results mostly of the suboblique subduction that forms this kind of transpressional oblique slip, reverse, and thrust faults, and strike slip systems, such as the most important one that you can see it in here in black, in a black line, that is the Lekinyovki fault zone. And this major structure of about 1,200 kilometers long mostly controls the location of the active volcanoes along the Southern Andes. But the Southern Andes are not only unique in terms of their tectonic setting, they are also a special geographic, ecological, and cultural area of the planet. Geographically, this part of the Andes consists of continuous but lower altitude mountains compared to the Central Andes, for instance. And most of the volcanoes are the highest mountains in this part of the mountain range. This region is also known as Northern Patagonia. So we have a rainforest that is ubiquitous everywhere and is difficult to penetrate. Also, the last glacial period shaped the valleys and sourced the sediments that now fill the forearc. And those sediments are now dissected by meandering rivers that occupy most of these midlands to coastal regions. And there are also many substantial lakes that are of glacier origin. To the east, crossing the Andes, vast pampas with cold steppe vegetation are found in Argentina. One interesting thing is that native communities, such as the Mapuche people, occupied both sides of the range before the arrival of European communities about a century ago. And the major cities are mostly placed in the forearc or the back arc, but not immediately in the arc, so not immediately threatened by volcanoes, as smaller rural communities do. So in the recent history of the Andes, of the Southern Andes, we can look back and see many interesting eruptions that have occurred. For instance, this one, the first one in 1979, that produced the birth of a new volcano. This is Mirador volcano. And this eruption lasted for about 3 months. Also, there was a conforming eruption in 1989 in Lonquimay volcano, producing this beautiful volcanic edifice, Volcan Navidad. And a part of those tiny eruptions that were mostly strombolian in eruptive style, we also had some very big eruptions, such as this one, the Hudson volcano eruption that is pretty famous in 1991, that produced a Plinian deposit towards the northern Patagonia region and erupted about 7 cubic kilometers of tephra. Also, in 1932, there was another Plinian eruption that occurred in the northern part of the Southern Andes, and in Quisapu volcano erupting dacitic magma, and it produced a deposit that is today preserved, and its volume is about 9 cubic kilometers. So if you compare the southern volcanic zone of the Andes with the central or austral, you will see that there are many reports and confirmed eruptions. So red dots are confirmed eruptions, and reports of eruptions by people are those black stars. And you will see that there is a huge amount of eruptions occurring in this part of the world, about or at least 60 historical eruptions in this part of the world. This is the work of Amigo in Volcanica last year. But we want to talk about the most recent eruptions and how they change the view that we have, like volcanologists, about volcanoes, about how they work. And this modern view of those volcanoes has occurred mostly in the last 15 years, at least in the Andes. So since 2008, there was an increasing number of volcanic eruptions in this region of the planet, and many of them were really important in terms of their impacts. So blue Texas, blue names and dates of eruptions correspond to strombolian or violent strombolian eruptions, if you like. The red ones correspond to Plinian eruptions, and the black ones correspond to phreatomagmatic, phreatic, or volcanic eruptions in this region. So Llaima was the first erupting, and months after there was an eruption in Chaiten, and then a series of numerous eruptions in Peteroa, Hudson, Cordón Caulle, Copahue, Villarica, Calbuco, Chaitén, and Peteroa. And I will not discuss this aspect in this presentation because this is about explosive volcanism. But if you are interested to know why so many eruptions, you can read a couple of papers that have been coming out about the relationship between megathrust earthquakes in this region and the volcanic response after those large earthquakes. So volcanic activity includes these eruptions, these plenary eruptions occurring in 2008 to 2011 and 2015 in Chaitén, Cordón Caulle, and Calbuco volcano. And as you can see in the images, these were very powerful. And I will give you an update of what we know about those eruptions and their impacts. So the first, Chaitén erupted after about 2 days of seismicity. Was a very intempestive eruption, if you like, and very intense as well. So at the very beginning, there was not clarity of which volcano was erupting. So Chaitén is located near the coast in this part of the bay of Chaitén. So this small volcano is Chaitén, and this big one, monster, is Michimahuida volcano. So everyone was thinking that the first, at the very beginning, that the volcano erupting was Michimahuida, but the column was so wide that was unable to show the volcano that was erupting at that moment. Finally, it was Chaitén. And it was believed that Chaitén was dormant by 9,000 years or so, but that's not correct. And the signs coming after the eruption have shown that this volcano was erupting about 300 years ago. So it produced the evacuation of 5,000 people that was living in the city of Chaitén, and costed about $48 million. And as this eruption was so big, a plenary eruption lasting for several days, there was a major concern about having a huge collapse of the column, producing enormous PDCs that could vanish Chaitén. So radius of 30 and 50 kilometers around the volcano were implemented by the authorities. But finally, this helped to evacuate all these people, and Lahar occurred days after the eruption, producing huge damage of the town that was cut by the half. And also the eruption produced more than 480 kilometers of forest destruction in the proximal area, with shortages on electricity and water supply in Chile and Argentina, and hundreds of flights canceled and airports closed. So here we have some of the images of this eruption, and you can see the situation that was produced in the city of, or in the town of Chaitén, with this huge lahar that came down and destroyed most of the city. And in Argentina, lots of villages were affected by the ash fallout. And the primary response was made by a team of the USGS with Chilean volcanologists. And in this VDAP program, so the assistance from the USGS was required by the local and authorities and volcanologists. And after that, there were a few papers published about the deposit, the Tefra deposit. And today, I think this paper of Alfano is one of those that shows the best or most accurate distribution of the Tefra fallout deposit. Interestingly, this deposit is not very coarse in the proximal area of the eruption, so it has no more than a half a meter, and it is very fine and composed for a complex stratigraphy, a multi-layer deposit. So it shows how some plinian eruptions, rhyolitic eruptions, can occur and produce proximal and distal deposits like this one, which is about 1 cubic kilometer in volume. The next eruption was produced by Cordón Caulle in 2011, 2012. And this one produced the evacuation of 8,000 people from Argentina, mostly, and also from Chile. And it costed nearly $700 million. And there was a huge mortality of livestock. About 50,000 of them died, and many roof collapses, water supply shortage, and transportation disruption in roads, in navigation, in lakes, but also and mostly flights canceled and airports closed, with long-term remobilization of the ash. I think if you are interested in the long-term impacts of this eruption, you can read some of the papers from Elizondo and her group, or maybe Pablo Forte, that made a nice work there in ash remobilization. So a very impactful eruption, mostly affecting, again, the eastern part of the northern Patagonia region in Argentina, but also affecting Chile. So here you can see the impacts of tephra rafts or pumice rafts. It depends on how you want to call it. Also the lahars that were very destructive in the proximal area towards Chile, and the impacts in the livestock and the tephra deposition in the proximal area around the vent. And in addition to the airfall tephra, there was also a lot of production of pyroclastic density currents. And this is an aspect that hasn't been studied in detail right now, but those pyroclastic density current deposits are still found in the headwaters of Nilagua River towards the north and northwest of the vent. And the deposit produced by this eruption was also complex, composed of many layers of pumice, showing the variations in the energy of the eruptive column, but also this deposit had a difference with the Chaiten because it was coarser in the proximal area. So nowadays you can find deposits that are about 4 meters thick near the vent area in the Cordón Caulle site. And this deposit was more volumetric than the Chaiten. It was about 1.3 cubic kilometers of bulk tephra, as shown by Marco Pistolesi and his group, and Bonadonna as well. And finally, we arrived to the latest plinian eruption that the Southern Andes has experienced, and this was the Calbuco eruption. And more than 6,000 people were evacuated. It cost us not too much, but nearly $20 million, and 450 houses were damaged, with more than 3,000 livestock evacuated. This eruption affected a lot the roads and also the facilities that were located around the volcano that were destroyed by lahars. And by that reason, the authorities secured a radio of 20 kilometers around the volcano by at least a couple of weeks. and many flights were canceled. In this case, the eruption produced this kind of damage by pyroclastic flows, lahars, and also the tephra deposition that produced a lot of roof collapses. So the tephra of this volcano was, compared to the Chaiten or Cordón Caulle, very heavy. It was andesitic and full of crystals. So it produced a lot of roof collapse given the density and the impact force of those particles. And in this case, again, the tephra went to the northeast, affecting Argentina, mainly Neuquén area, but also a part of the Chilean Andes. And the volume was calculated by our group in about 0.3 cubic kilometers, I will say with more certainty. The magnitude of each eruption, of each subplanar eruption that I have shown here is almost the same, about 4.4 or 0.6. And this eruption, the Calbuco one, was more intense than the Cordón Caulle one because the columns were higher, about 23 kilometers height. And the deposit was very simple. Despite it is multi-layer and has differences in the grain size and density of the particles in a vertical section, this is not as complex as the Chaiten or the Cordón Caulle deposit. And there was a lot of coarse material being deposited in the proximal area, just producing accumulation of about 15 meters height in the very vent of the eruption. So those eruptions were very, very important for volcanology, modern volcanology, and I will show you why. And I will also mention some of the other eruptions, the smaller ones, and how they have also changed our perspectives as scientists. So I will for sure mention the Llaima 28 eruption, the Villarica 2015, the Chaiten 2016 to present eruption, and the bigger ones. So starting from Llaima volcano, what we have learned from this mate? Well, Llaima erupted a special type of pyroclastic fragment during its eruption. I'm pretty sure you have seen many of those in the field. So it is called platyscoria, and tephra or platyscoria was interpreted by the team of Ruth and Calder as formed during the rupture of large gas slugs associated with the unsteady fire fountaining activity during strombolian eruptions. So they interpreted this kind of process, and here you can see the diagram that they have done to interpret this fragmentation of the materials. And studying in more detail the tephras, they reached to the conclusion that the magma of Llaima is always receiving a lot of small intrusions. So the chamber, the reservoir, is always subject to a lot of replenishment, but it doesn't produce many eruptions. It only erupts when there is a big magma intrusion in the chamber that produces a lot of degassing and overpressurization, and then finally eruption. So in this case, the system is a little bit different to other basaltic volcanoes, but is an open vent system. So most of the time when it is receiving this kind of small magma batches, it is degassing. But finally, when a big magma injection comes from depth, it is able to produce a pure paroxysmal eruption like that observed in 28. So the larger the magma recharge, the highest the explosivity of the eruption in the case of Llaima. And this is different to what we have seen in silicic systems. For instance, in the Kisapu volcano that I was mentioning before, where the small magma intrusions may produce really, really big eruptions in those systems that are already accumulating pressure. On the other hand, they used olivine diffusion chronometry to establish magma intrusions that occurred at least 4 years before the eruption. So it took a lot of time to prepare this volcano to erupt. And about 6 months before the eruption, the new intrusion reached the storage or the shallow crust storage level prior to erupt. Another similar system is Villarica, and Villarica is interesting because it is an open vent volcano as well. It's a basaltic system. It has a column of magma that produces a lava lake that is almost every time of the year visible from the crater rim. And it is always changing its level and producing a small puffing, small eruptions, but not frequently erupting in a vigorous way. Not at least since 1984, when it was the last big eruption of this volcano. So it erupted again in 2015. And the first group, I think, to study this eruption was that one of IUPA, and they used multi-gas sensors to interpret the ascent of overpressure gas bubbles originating from shallow pressures as the driver of the 3 March 2015 eruption. Now we are carrying a study on those samples and samples collected after this period of the activity. And this work is under review in Bulletin of Volcanology right now. And we show that the lava fountain activity was fed from a deeper and hotter basaltic andesite magma, which experienced long-term magmatic evolution in near equilibrium conditions, and then billion ascent in the upper crust. And finally, the eruption seems to be triggered by volatile saturation and overpressure at very shallow depths, about 800 meters below the surface, triggering magma acceleration and fragmentation for sure. So this picture is very similar to what we can see, or at least we can compare it with the situation in other open vent systems, such as Etna or Stromboli in Italy. So that's interesting. But there were also other improvements in the knowledge of this kind of eruptions. The group of Jeffrey Johnson, for instance, has implemented infrasound instruments in this volcano many times. And these instruments have shown a great advantage to detect and characterize the lahars, but also to determine the position of the lava lake within the conduit. So it started to rise days before the eruption, giving a very powerful precursory signal before the eruption. And they have also used through machine learning algorithms a system to detect and classify the type of volcanic activity in the crater. So they use surveillance cameras to study the type of activity and the plume velocity in in time series, which is important as well for visual observation of the activity that is mostly described by volcanologists, but in this case, you can quantify the type of activity that this volcano is producing. So in this case, we have studied the Teflon deposit that is very, very small. It's about 2.5 million cubic meters, and yeah, as well these pre-eruptive conditions that we hope to get published in a bit. And when volcanoes erupt, like in the case of Llaima and Villarrica, they also increase the interest of scientists on their past. So many studies have came out to describe the historical activity of those volcanoes, as well the Holocene activity and the compositions, the magma plumbing systems, and the triggering factors for the eruptions that they have produced. So, for instance, this is the mafic Curacautin ignimbrite in Llaima volcano, which is about 8 cubic kilometers, according to Marshall and Valdivia papers. And this eruption has been explained by rapid magma ascent. So this is an important insight on how those mafic ignimbrite deposits can be produced. But in the case of Villarica, that has produced 2 mafic ignimbrites, the Pucón and Lican ignimbrites, researchers have found that the most likely event that can produce them is mixing between more evolved magmas and deeper, less evolved and gassy magmas rising through the crust. So this is an important insight as well. And we also know a little bit more about the plumbing systems of those volcanoes. So in the case of Llaima, the long-term compositional variations likely result from stress regime variations, because that volcano is just over the Liquiñe-Kefauver zone. Contrarily, Villarrica is not in the Liquiñe-Kefauver zone, and the recent models propose more complex transcrustal magmatic systems and mixing events between different magma batches that can explain the chemical variability of this volcano. And apparently, the modern activity of Villarrica is sourced by shallow and more primitive melts that mix the gas in the shallow subsurface before the eruption. I will just mention these tiny eruptions that have occurred as well in the Southern Andes in the recent years. This is Copahue volcano, and I put it here together with the Planchón Peteroa volcano, because they are both mafic as well. So they produce trachybasalt, trachybasaltic andesite, and basaltic andesite products. So here you can see how this volcano has been erupting since 2012, producing phreatomagmatic manifestations and purely magmatic manifestations throughout strombolian eruptive styles. This is very close to Capiahue, a small town in Argentina. So it is a hazardous volcano, and it is an important volcano for that community that needs more monitoring in case of an eruption. And Planchón Peteroa has been erupting twice in 2011 and then in 2018, producing this phreatomagmatic activity. This volcano has a lava lake or many lava lakes in different craters on the summit. And most of the studies of those eruptions are related to the question of when the juvenile materia comes out and what kind of fragmentation processes are occurring within the conduit, and even more the storage of the magma beneath the volcano. And we also can mention this Chaitén eruption that is ongoing right now, is erupting at least several times a day. And this volcano in the Southern Andes is andesitic, is different to the others that I have just mentioned. And the first work of Muslim in 2018 was trying to also answer this question of when the juvenile materia is coming out. They used gas emissions and also petrology to understand the system, and they produced 3 different scenarios that fortunately we can see today occurring in the volcano. And these scenarios involve the sporadic eruption and breakout of the lava dome that is on the top of this system. So many papers have come out about the ascent and rupture of lava domes, and the seismicity related to those processes, as well as geodetic other geodetic information as deformation, also remote sensing of those eruptions, also the growth and evolution of the dome has been studied in detail, and the tephra samples in a manner of a petrologic monitoring of this eruption. So it's great to see this evolution in time, because today we are now able to see, or at least to understand better, the plumbing system of this volcano that was not clear before the eruption, both from petrology, but also from geophysics. So now I will just mention the bigger eruptions that we have experienced. So as I told you before, I give you a summary of what happened in Chaitén, Cordón Caulle, and Calbuco, but now I will describe how these eruptions have been important for the science. So Chaitén in 28 demonstrated that even rhyolitic eruptions can be preceded by very, very little warning, as magma is able to ascend from depth rapidly, in this case at 1 meter per second, according to Castro and Denwell. To reach the surface from about 5 kilometers depth in only 4 hours, the magma should have been segregated and stored along existing crustal faults before intruding as a dike. So that's what we can see from this work from Weeks 2011. Geodetic data describes at least 4 different magma sources to feed this eruption. So the system beneath the volcano is also very complex, even to produce a very homogeneous rhyolitic composition when erupting. The experimental research of Chaiten samples, and this is very important, has shown that rapid cluster expansion under low pressure conditions may be important for explosive magma fragmentation. So Pablo Forte showed us in his paper that only with an initial content of 1.4% of water and a magma temperature of 874 degrees Celsius, the magma behave as brittle, producing explosive fragmentation. So this can be applied to many other rhyolitic eruptions elsewhere. And ultimately, the rapid decompression produced by the failure of the pre-existing lava dome on top of this volcano may have triggered nucleation of vesicles and explosive fragmentation, as shown by Alfano in his work. Another thing that I can mention is that this volcano, just after the depletion phase, produced a huge lava dome, about 1 cubic kilometer in volume. And this dome seems to have been extruded at a very, very high rate. So reaching about 66 meters cubed per second, among the highest ever measured on the Earth for silicic magmas. And this effusive stage could have been triggered by buoyant ascent of the magma, as there is no deformation during the emplacement of the lavas. On the other hand, we have Cordón Caulle in 2011, and this eruption raised questions about the conditions leading to explosive effusive transitions of rhyolites and rhyodacite. As in Chaiten, Castro and his team identified the source of the magma at less than 5 kilometers depth, and it was a relatively hot magma, more than 870 degrees Celsius up to 920 degrees Celsius. So these conditions may have allowed the magma to initiate an eruption very, very rapidly through the dike. Despite the composition, this lava seems to be much more similar to basaltic counterparts as consequence of their high thermal efficiency. So just after the eruption, we can see the lava flow coming out from the volcano. And this is pretty much the same in terms of morphology and textural characteristics to basaltic lava flow. And that's very interesting. So in this case, I think, and what these authors say is that these lavas maintain the thermal energy for quite a long time. And the ductile extrusion of the lava also benefit the horizontal flow, producing a huge lava flow, or maybe we can call it like a lava field. And the Cordón Caulle showed us that there is an interplay of both ductile and brittle processes that accommodate producing the kind of activity that we observed during the eruption, like this gas jets, and also volcanic blasts and lava effusion, everything at the same time. So there are several models for this related to gas segregation and fracture opening and permeability of the magma in the conduit, but also other models that recall for the role of sintering of ash within the conduit that may have controlled the effusive stage beginning after the eruption in 2015, sorry, in 2011. So the overall eruption is also found that was fed by intermediate to evolved magma pockets, as observed from ash grains in the paper of Alloway in 2015. And for sure, this shows that this kind of eruptions, even when producing a very homogeneous material, may be sourced by different magma pockets. Whereas Winslow has shown recently that the crystal poor rhyolite was derived from a single differentiation step from basaltic composition to rhyolitic composition. So that's very interesting as well. And finally, we have Calbuco eruption. And this is important because it was a sudden eruption. There was just a 3-hour seismic storm before the eruption. And it was not very clear to show to show us that there was something nearly to produce an eruption. So almost looking clear precursors, at least two models have been proposed. The first consists in the internal triggering by pre-exhaust volatile overpressure, I will say water, SO2, CO2. And this model requires a closed system magma chamber that can evolve and produce a second boiling event. And on the other hand, there is a second model that includes thermal heating or underplating of the magma chamber by possibly a mafic and hotter localized magma, triggering the overpressure and eruption. That's the model of Morgado and collaborators. Despite this, there's a chance that both models are complementary. So according to Namur, there is a possibility that weeks or months before the eruption, the mush may have disaggregated, maybe by underplating, releasing crystal-rich dacitic melt that ascended to shallower levels, producing the eruption at the end. And this eruption has raised the importance on understanding the magmatic system beneath Calbuco. So to date, the best fit model indicates that those mantle melts that produce the magmas of Calbuco are able to produce high silica, high alumina hydrous basalts, primary melts that fractionate, forming these compositions. And in addition to what we know about how those systems work from the inside, there are many works that have reported now the processes that are related with those eruptions as well, like pyroclastic density currents. So dilute PDCs and block and ash flows were common during the Chaiten eruption, and both produce partial column collapses and lava dome collapses that are now very well described in this work of Mayer and Swanson. Contrarily, little or none is understood about the PDCs produced by the Cordón Caulle eruption in 2011, as I mentioned before. And at Calbuco, PDCs occur during the two eruptive pulses that it had and reached at least 540 degrees Celsius. And this is a work that we are preparing right now. And the interesting thing is that in a vertical profile, you can find that there was a higher cooling rate in the bottom of the deposit towards the surface. So this deposit was cooler in the bottom, and charcoal is only found in the upper part. And we thought this was produced by the entrainment of water, external water, that was able to cool down the deposit from the bottom to the top. And as well, the 2015 eruption of Villarica raised the importance of understanding the processes that occur in ice-clad volcanoes, like this mixed avalanche deposit. So Vera and Palma and Bert have studied quite a lot the generation of these mixed avalanches from PDC deposit, from PDCs to Lahars, or even from the agglutination of sputters near the vent that may collapse and produce this kind of deposits that are very interesting and very important when they produce lahars. And an additional outcome of all this research is tephronology. So since 28 eruption of Chaiten, at least 20 eruptions have been identified as sourced by Chaiten volcano in the last 18,000 years. So the volcano was not even close to be dormant for 10,000 years. It was erupting with a high frequency every 200 or 300 years. And that's very important to understand the hazards of rhyolitic eruptions. On the other hand, at Cordón Caulle and Antillanca, Naranjo has identified at least 5 voluminous tephra deposits that preceded the 2011 eruption. And those Plinian deposits, some of them reach 9 cubic kilometers in volume. So they are very powerful eruptions. And our recent work in Calbuco volcano has shown that at least 12 eruptions are preserved in the historical stratigraphic sequences in the proximal areas of this volcano, also including pyroclastic density currents that may have surpassed the high topographic barriers in the volcano. So very interesting findings. And for sure, this work of Alloway in 2021 that also takes into account a lot of works that have been made in the Southern Andes in the recent few years, is able to reconstruct the tephra deposition in this northern Patagonia area, and the paleoclimate, and also the soil formation rates during the last 14,000 years. So very interesting stuff for the earth sciences, assisted by explosive deposits of those volcanoes. So what is being doing in terms of volcano monitoring in Southern Andes? Argentina has a new program that came out in 2017 with the building of the Observatorio Argentino de Vigilancia Volcánica. So this is the first volcanological observatory in Argentina, and they assist the SEGEMAR or Servicio Geológico Minero Argentino. And they currently monitor just 2 volcanoes, Planchón Peteroa and Copahue, that I have shown here. They only have seismic and geochemical monitoring right now, plus remote sensing, but in the future they are planning to monitor many other volcanoes that are considered of high interest because of the threat potential for Argentinian communities. In terms of the Chilean case, this volcanic hazard program came out in 28, just after the eruption of Chaitén. So this was born by the interest of civil authorities to produce a learning about volcanic emergencies and a robust system to monitor volcanoes along the Southern Andes. So they created this volcano hazard program and the Southern Andes Observatory, and they currently monitor 45 volcanoes with seismic, geodetic, and remote sensing tools, but still limited for geochemistry and petrology. And the aim is to improve eruption forecast, to develop an early warning capability, and to assess the volcanic hazard. And regrettably, we have to say that despite having 45 volcanoes under monitoring right now, this is only the half of volcanoes that we need to monitor because this region is full of volcanoes. And scientific collaboration is very, very important. So hands have helped us, like South Americans, during the huge crisis that we have experienced in the last few years, from the States, from Europe, from also from Japan. I have just put there some of the institutions that are important and are developing a lot of research in this area of the planet, but there are many other that are not mentioned there because of the size of the slide, for sure. And in 2016, we had the cities and volcanoes there in Puerto Varas, just after the eruption of Calbuco volcano. So there was a huge interest from the international scientific community to attend, to observe what happened in Calbuco, and for sure to build more intense relationships with our local community. And that's a powerful engine to move science. So right now, what's next? Multidisciplinary science, I think, is really important. Volcano ecology, some people is doing this in the Southern Andes, but very slowly, just in a few volcanoes, Chaiten, Cordón Caulle, and Calbuco mainly. Volcanic risk and communities. This is made also by British universities that are working there in the Southern Andes. They are talking to people, learning how they live, how they understand volcanoes, and how to cope with volcanic crisis. Health impacts of volcanic eruptions are really, really important, especially in the Argentinian side, because they regrettably suffer a lot of ash deposition. And for sure, there is a need to understand better river and landscape dynamics after the eruptions, to implement more geophysics and remote sensing monitoring on those volcanoes, and to preserve and create geoheritage from those volcanoes. We have right now the first national and probably one of the first in Latin America geoparks that for sure it was born in a volcanic territory in Llaima volcano. So that's really, really important to preserve what volcanoes and their surroundings mean for those Andean communities. And for sure, this is important for paleoclimate and soil science, rock engineering, and many other areas of geoscience. So that's our next step, but we are far away to be in a good position to say next eruption will not produce any more deaths. So that's a real problem today. So that's my presentation. Thanks so much. And I have at least 6 slides of references that I will briefly show you here. Thank you.
Thank you very much, Jorge, for your great presentation, for this overview that you gave us of the explosive activity in volcanoes of the Southern Andes. So we have time for questions. So if you have any questions, so there is the Q&A, so you can write questions, and then I will read those questions to Jorge. So while we wait for question, I have one. So you have shown several things that need to be done in the future, or things that scientists are working on. So in your opinion, what is the priority to improve the knowledge of these volcanoes, and also to improve the hazard assessment?
Yeah, I think a key priority today is to implement more laboratory capabilities to study those volcanoes right there, because in most of cases we need to, and also as researchers, we need to go to Europe, to the States, to Australia, or many other countries to take or get the tools, the necessary tools to learn about volcanoes, and to work on the samples that we collect to monitor volcanoes as well, because we have a lot of instrumentation, for instance, seismic stations, but not all of them are made to monitor volcanoes. So, you know, we have a huge network for earthquakes in Southern Andes, but this network sometimes has to assist the volcanic monitoring in the case of Chaiten, for instance, there were just 2 or 3 stations, 200 or 300 kilometers away from the volcano. So that's a real problem for us.
So thank you. Is there any other question from the audience? So you can use the Q&A to write your questions.
Sorry, Mattia, I want to thank Jorge, because we know that during these weeks he's working on his PhD thesis. So thank you very much for this very nice talk.
Thank you so much. I'm happy to show you this, and this is part of my work. I didn't want to show just my stuff, because there is a lot of people working there getting amazing results, and I think that's a more powerful story to tell you, and more important, because papers tend to accumulate in the desk, but we have to sit down and try to think about all the findings, and then to compile a story and see what we learn from these eruptions after they have occurred. And fortunately, there were not deaths after those eruptions.
Oh, sorry, can you hear me?
Yes.
Okay, so we are collecting questions now. So the first one is from Felix Boschetti. Thanks, Jorge. Some superb images and discussion of the volcano science in the SVZ. It's very clear that recent eruption drives scientific interest in volcanoes in the region. Do you think there is a volcano that is generally considered inactive or low activity and therefore hasn't had the attention it deserves?
Well, that's a good question. We have many volcanoes with those characteristics, and probably, well, in the 90s, early 90s, there was a huge effort to do Teflon stratigraphy in the Southern Andes. And many of the volcanoes that we now consider to be the most active and more risky for people are those that had this kind of signature in the geological records. But the problem is that many of the volcanoes are inaccessible, and they don't have this kind of preservation of tephra layers, for instance. And there is not a huge interest to study them, because they are believed to not be so active. So this is the situation of many of the volcanoes that lie in the northern part of the Southern Andes. I will say Tupungato, San Jose Maipo volcano, and also Palomo. We have many ones. And those volcanoes tend to be more silicic than the southern counterparts, and for sure can produce very big eruptions. If I can mention that, for instance, this San Jose volcano lies very close to Santiago, the capital of Chile. It's about 70 kilometers east from Santiago, and this is not very active. It is always having some fumarole activity on top, and is very high, very voluminous, and the map today includes also debris avalanche production from this volcano that can happen in a future eruption. So we have to look carefully if our ranking is based on what we know about volcanoes, or what the volcanoes really represent for their communities. And for sure, I didn't went. I did not try to go into the details of Laguna del Maule volcanic field that is very big, very active. It's having a huge inflation process during the last few years, and yeah, it could erupt and produce eruptions easily with 10 cubic kilometers of rhyodacite tephra, for sure. Yeah, I hope to answer your question.
So thanks, Jorge. We have a second question from Modesto Portilla Gamboa. Are only the big earthquakes that have been occurred in Chile the responsible for the volcanic activity observed after them?
I will say no, for sure, because yeah, we can see changes in the stress fields after the big earthquakes in the arc, in the volcanic arc, but this is not a big response of the crust when earthquakes occur. It is mostly about volcanoes that are ready to erupt. So, for instance, Cordón Caulle was experiencing a pre-eruptive process since 27, I think, so many years before the eruption. And then you have the earthquake in 2010, and just 1 year or so after, you have the eruption, but it was probably reactivating the ongoing process that was occurring beneath the volcano. And many other examples as well in Calbuco in the 1961 eruption. It occurred just after the earthquake in Valdivia, the biggest one in the human history. But there is not a causal explanation for that, and it looks like it was probably a second boiling eruption, like the last one. So yeah, probably there is some coincidence and some causal relationship in some of those volcanoes that are ready to erupt, but in general, the volcanic process is ongoing when the earthquake gives the last push.
Thank you, Jorge. So there is a last question, which is more a technical question, not really for you. So from Joel Wick, thank you, appreciated your presentation. Hopefully the recording will be available. And so as regards this question, the recording should be available on the IAVCEI website, but it's available for the IAVCEI members. So as regard this thing, also the webinar usually are open to the IAVCEI members. So in this case, for this webinar, we received a lot of requests also from non-IAVCEI members. And so we opened the view and we allowed other people to participate to the webinar. But please, if you want to support this kind of activity and if you want to support IAVCEI activity, renew your membership, or if you have never been a member, so become a member of IAVCEI, because this will help us to organize more activity, more webinars, conference, congress, and all the activities that the association is carry on. So we don't have other questions. So
no, Mattia, there is another question from Nick Varley.
Oh yes,
I have last question. It was down.
Thank you, Daniele.
Okay.
Yes, so we have another question from Nick Varley.
It is clear. Oh, right, go.
Yes, it is clear that petrological monitoring is important and gives important insights. How fast can the results be made available by the different labs involved for Andes eruption? And is it fast enough?
I don't think it's fast enough. If we go to the instruments, I will say that we don't have a microproof in Chile, and probably there are a couple in Argentina that need more control samples to get better results. So that's a big point. We only have SEMs and grain size for sure, grain size instruments and thin sectioning labs, but that's not enough. So finally, to get results, it takes months, if not years, before getting a good result. This has been solved in some way working with the USGS, for instance, as we did in the Planchón-Peteroa eruption. And we got results during the eruption to tell the authorities what was going on the volcano, but is an exceptional case, especially when you have a big eruption that produces a lot of disruption in the system. So there is not a priority to study the samples at the very beginning, and there's not human resources to do so. So thank you, Nick, and I think you will be very interested in Chillán eruption as well, because it's very similar to some of the volcanoes that you have been studying.
So thank you for the questions. Thank you for to all the participants, and thank you in particular to Jorge for this great talk. And also to IAVCEI for giving us the support to this to organizing this webinar. This webinar was part of a series of webinars on explosive volcanism that was organized by the Commission on Explosive Volcanism. And our mandate, so Daniele and I are actually the leaders of this commission, but our mandate will end the next year, at the beginning of next year, and we would like to have to support the renewal of the leaders, and this should be done during the IAVCEI meeting in New Zealand. So if there is anyone who is interested in taking the lead, please send us a message or a letter of intent. And if there would be a large number of people from who are members of the commissions that will participate to the IAVCEI meeting, we will do that, the election of the new leaders in person. Otherwise, we will find a way to do that online. And if you are not members of the commission and you are interested in becoming members of the commission, you can send an email to us, to Daniele Andronico, and or to me, Mattia De Michele Vitturi. So I think that's all for today. Thank you again. Thank you, Jorge. And we hope to see you soon to the next webinar that we will announce soon.
Thank you so much. Have a nice evening.
Thank you again, Jorge.